talk about Venn diagrams? Alright, so if you recall last time we were talking about sets. So one way that we can just visually or with a diagram or pictorially visualize sets is using something called a Venn diagram. You've probably seen these used in other contexts as well. Like I know like in English classes, if you're trying to do a compare and contrast essay, lots of times they make Venn diagrams to show the relationships between certain subjects and things. So you've probably encountered something like this before. Okay, so in terms of a set, a rectangle is used to represent what we call the universal set. So the universal set is just all the things that are under consideration. So that could, if we were talking about this class, the universal set would be all the students in here. If we were talking about the university, the universal set would be all the students in the university. If we were talking about, maybe integers or real numbers, you can define whatever you want your universe to be, and then that's the only things that you're thinking about. Okay, so a rectangle is used to show a universal set. Those are all the things under consideration. And then circles or ovals, just basically not rectangles, curved kinds of shapes, we'll talk about what will be used to refer to a set within the universe. Okay, so you've probably seen Venn diagrams for the set of real numbers before. Here are the two most popular ones. Okay, so let's just kind of talk about what this means. So here, this rectangle here represents the real numbers. So here, this is the universal set is the real numbers. Okay, and then we see various, ellipses and circles, or whatever you want to call them, okay, that are inside. So this picture is telling us, I know the words are kind of small, but this little oval here is telling us that the irrational numbers, okay, so that's the symbol we use for irrational, right? Okay, is a set within the set of real numbers, R. So within its universe. So here we've got this oval that represents the irrational numbers. It's inside this rectangle. So that's trying to tell us that the irrational numbers is a set within the real numbers. Similarly, this one over here, this on the outside, okay, that's the rational numbers. So that circle on the outside is trying to tell us that the rational numbers is a set within the real numbers. Now within the rational numbers, there's other sets within there. So if I look at this one, for example, okay, that one's labeled integers. So that one's trying to tell us that the set of integers, okay, is within, and if you look outside of it, what contains it, that's the rational numbers. So that's telling us that the integers is a set within the rational numbers. Okay. And we could go down and interpret those others as well. Okay, so I'm sure you've seen that kind of a picture before. Now this one is very similar, but okay, notice that in this one we've got more rectangles and not just ovals like this one. So here, this rectangle here, this is representing basically I'll call it the rational universe. So this is a universe of the rational numbers. So this is a universe of rational numbers. That would be Q. And this rectangle over here is another universe. So this is the universe of irrational. So that would be like our Q bar. And then if I take this universe, this rectangle, and this universe, this rectangle, and put them together, this larger rectangle, the one that's that big, so that's, okay, these two universes together make up this universe of the real numbers. So that's our R. And then in terms of, these ovals in here, okay, they're similar to the ovals over there. One thing that's nice, sorry. One thing that's nice about this one instead of this one is when you look at this picture, kind of because there's this space around here, it makes you feel like there's maybe could be things out here that aren't irrational numbers and aren't rational numbers, but are still in the universe of real numbers. But there aren't anything out there. That's why, this one's probably a better representation of the actual universe of the real numbers, but you might have encountered either one of those. Okay. I like that one better. Okay, so if we can have a set that is inside of another set, and you guys already looked at this inside books, I think, because there were a few of these. Okay, that is the idea of a subset. Okay, so if every element of a set A is also an element of another set B, then we say that A is a subset of B. So this means that A is contained within B, or everything that's in A is also in B. Okay. So if everything in A is in B, and there's also something in B, so there's an element in B, and that element is not in A, then we call A a proper subset. Okay, there's a lot of notation there, but let's think about what that means. So A is a subset of B, so that means everything in A is in B. Okay, but then there's this other thing in B that's extra. It's in B, but it's not in A. So it's kind of, B is bigger than A. It has more stuff than A, because there's something in B that isn't in A as well. Okay, so there's no possibility of them being equal. So notice the difference between these two symbols here is there's no line underneath. Right, the line is missing because there's no possibility of them being equal. So it's sort of like, strictly less than or less than or equal to. Okay, so this one, there's a possibility that A and B are both exactly the same thing. Okay, so imagine if I just put A, every element in A is also an element of A. Sure, that would work. Of course, every element of A is in A. So if these were the same sets, it would still be true. So every set is a subset of itself. Okay. However, in terms of proper subset, no set is a proper subset of itself, okay, because it's equal to itself, and this does not allow the possibility of equality. Okay, so there has to be more stuff in B than in A for A to be a proper subset. All right, so we can evaluate our understanding. So we've got our little picture of a Venn diagram over here. Our universe is the set E in this rectangle. It's got a bunch of stuff in it. This C is supposed to refer to this one right here. I'm not sure why it's so far away. Okay. This one is A, this one is B. Okay. So if this is a proposition. A is a subset of A. True or false? True. Definitely true. So every element of A is also an element of A. We already decided that when we talked about subset. Okay. How about A is a subset of B? Well, for that to be true, every element in A would have to also be in B. Is that true or false? False. Okay, so can you find a counterexample? Okay, so 2 is not in A, so it's not. So here, okay, it's kind of like if it's in A, then it's in B. So think about like, if in A, so I have to have a true hypothesis, it has to be in A, then in B. False conclusion would be it's not in B. So can I find something that is in A, but not in B? 1, yeah. Okay, so A is not a subset of B because, 1 is in A, but 1 is not in B. So this one is false. How about is A subset of C? Everything in A is also, if it's in A, then it's also in C. False. What's your counterexample there? 4. Good. So here we have 4 is in A, but 4 isn't in C. So we don't have the case that everything is, if it's everything that is in A is also in C. Okay, so this one is false. We won't do counterexamples for all of them, but all right. Is C a subset of A? So everything in A is an element, everything in C is an element of A. I see heads nodding. Yes, it is true. So there's only 2 things in C, 1 and 9, and they're both in A. So yes, this one is true. Is B a subset of A? So is everything in B also in A? No, there's a whole bunch of stuff over here that's in B but not in A, so this one's false. Okay. Is the empty set a subset of A? So that everything in the empty set is also in A. Yes, of course. Okay. So one thing to note here is that the empty set is a subset of every set. Okay. So the empty set is a subset of every set. Okay. Because every set contains at least nothing. Maybe more, but at least nothing. Okay. If we're going to call it a set, it at least has nothing in it. Okay. Is C a proper subset of A? I see a few head nods. Yeah, so remember, proper subset would mean everything that's in C is in A. We've already established that's true. But there's at least one extra thing in A that isn't in C. So notice over here in set A, 4 and 16 are both in A, and they're not in C. So we do have extra stuff in A that isn't in C, so it is a proper subset. Okay. Is A a proper subset of itself? No. Remember, if we're missing the little equality under there, we're not allowed to, there has to be extra stuff. So is there any extra stuff in A that isn't in A? Of course not, right? There can't be any extra stuff. All right. Is the set containing the empty set a subset of A? This is where it starts getting tricky. So let's go back to the definition. Okay, so for it to be a proper subset, first of all, it would have to be a subset. So we could just check that first. And to see if it's a subset, we'd have to go through every element of the first set and check to see if it's an element of B. Okay, so how many things are in this set on the left-hand side? There's one thing in there. Okay, there's one thing in there, and that is the empty set. So I'm going to go over to the set A and look. Can I find that in this set? Can I find the empty set in there? No. I've only got numbers in there. 1, 9, 4, 16. There's no sets in there. Okay. So, no. The set containing the empty set is not a subset of A because the empty set is a subset of this one. But the empty set is not an element of A, right? So I found something in here that's not in there. So not every element in this set is in that set. Okay. I know that that's a little bit tricky. Question, does that make sense? Okay. The element that's in here, in this set, is a set itself. It's the set containing nothing. And when I go and look in here, there's no sets in there as elements. There's only numbers, but there's no sets. I would actually have to see the empty set as an element in there for this to be a subset of that. So, that last example leads us to the fact that we can have sets that contain other sets. Okay. So, if we define a set A to be this set. So notice the outer brackets here. So this is roster notation. I have the outer brackets, and then the elements are listed with commas in between. Okay, so I've got something and then a comma, so that's a comma, and then something and then a comma, and then something and then a comma. So these are the elements. Okay, those are the things between the commas. So I've got the brackets on the outside, and then the things separated by commas are these things. So I've got a set and another set, so 2 of the elements are sets, and 2 of the elements are just plain old integers. Okay, so what's the cardinality of A? 4. It's got 4 things in it. The cardinality is how many elements there are. So there's 4 elements. Okay, so is 1 an element of the set A? So if 1 is an element, it should be one of the things that's listed between the commas. Is 1 an element of the set A? Yes, it is, right there. Okay, it is an element, so that is true. Okay, is the set containing 1 an element of A? It's got 4 elements. Look at them and see if you can find that as an element. No, you can't find it, right? It's got a set containing 1 and 2. It's got the integer 1, it's got the integer 2, and it's got a set containing 0. None of those are the set containing 1. So that's not an element in the set. So this is false. It is not an element. Okay. Is the integer 0 an element of set A? Nope. Okay. So that's not 0, that's not 0, that's not 0, and that's not 0 either. Right? It's not in there. Is the set containing 0 an element of A? Yeah, that one is there, right there. Right? Is the set containing 1 and 2 an element of A? Yes. Is the set containing 1 and 2 a subset of A? So let's think about what this means. That would mean I'd have to go through every single element in this set and check and see if it was in this set. So, is 1 in the set A? Is 2 in the set A? So is this set a subset of this set? Yes. So 1 is there, 2 is there, and of course this is a proper subset. Is there any extra stuff in A? Yeah, there's some extra stuff. So yes, this one is true. Okay. Is the set containing 0 a subset of A? No. Okay, so I'd have to go through here and see, is everything in this set in here? So there's only one thing in there, 0. Is 0 an element? No. The set containing 0 is, but not 0. Okay, so that is not in the set, so this is not a subset. Okay. Is the empty set a subset of A? Yes, and we said back here, the empty set is a subset of every set, right? So that should be, as long as we know that fact, that one shouldn't throw us off. Yes, so everything in this set, which is nothing, is also in this set, because every set has at least nothing. So yes, that one. Is the empty set an element of the set A? It has 4 elements. Is one of them the empty set? No. Yeah, so this is not an element. Okay. So notice the difference between an element and a subset. Okay. So when you're looking, whenever you see this is an element of, whatever's listed right there, you're looking for that exact thing in the set. So notice here, 1 is an element because I found it. It's right there. This set containing 1 is not an element because there's only 4 of them, and that's not one of them. Okay. This one is an element. Again, there's only 4 of them, and that's not one of them. So with an element, I'm looking for this exact thing in my set. Subset is different. Okay, so if I'm checking to see if it's a subset, I'm going to go in between the parentheses, and I'm going to look at all the elements that are listed in there and see if all of those elements, okay, appear in that set. So I'm not looking for the set itself, I'm looking for the members of the set. So I know that can be a subtle difference, but if you just keep track of, with the element, I'm looking for that exact thing as one of the elements in the set. With subset, I've got to go through the whole list and check are all of these in the other one. So when I give you a quiz on this, it'll be very fun. Okay. Next, we have the concept of a power set. So the power set of a set, so denoted with a capital P, and then in parentheses, you just put the set that you're trying to take the power set of. So this notation right here means the power set of A. Okay. Is the set of all possible subsets you could make with elements from A. Okay. So let's go through some examples. So I have A that is the empty set, there's nothing in it. I've got a 1-element set, a 2-element set, a 3-element set, and we'll practice making all the possible subsets that we could make. Okay, so let's do the power set of A first. Okay, and if you do it in a systematic way, it's not too hard to generate all of them. Okay, so the smallest possible subset you could have would have nothing in it, 0 elements. Okay, and we know that, so I'm going to list all the sets I could possibly have. Okay, so the first subset of the empty set is the empty set itself. Okay, that everything in this set is also in this set. Okay, are there any other subsets of A? And that's it. There's nothing in there, so the only subset is nothing. The set containing nothing. Okay, so notice that the set A has cardinality what? So the cardinality of A, is actually 0. There's nothing in there. The cardinality of the power set of A, down here, what's that? That's this one. How many things are in this set? Just one. Right, so the cardinality of this, how many things are listed in between the brackets? 1. It's a set, so that's cardinality is 1. Okay. Let's find the power set of B. Okay, that's going to be a set of all the possible subsets. Okay, well we know that that the empty set is a subset of everything. That's the only set of size 0. Okay, so there's a subset of size 0 that is a subset of B. Okay, but there also could be a set of size 1 that has one thing in it. Okay. All right, so we also can have a subset that contains just 0. Are there any other subsets? There's nothing, or there's this element. And that's really the only possibility. Subsets of size 0, subset of size 1. There's only really one subset of size 1. Okay. So what's the cardinality of B? 1. That's got one thing in it. What's the cardinality of the power set of B? 2. Okay. Let's go with the power set of C. So it's going to be the set of all possible subsets. Okay, so it's got the empty set in it. So that's the only set of size 0. And then it could have some subsets that only have one thing in them. So it could have a subset that only contains 0, or it could have a subset that only contains 1. These are the only possibilities for subsets of size 1. We've exhausted those. But we also could have a subset that contained 2 things. So that could be this set that contains 0, 1. Well, this only has 2 things. We can't have any bigger subsets. So we've exhausted the list there. So what's the cardinality of C? 2. And what's the cardinality of the power set of C? 4. Okay. we get up to the power set of D, I'm going to kind of list these on multiple lines, so hopefully it won't throw you off, but when you start getting to lots of them, sometimes you need a systematic way to organize it. So all the subsets with size 0 is just the empty set. I'm just going to put those on one line. Okay. And then I can have subsets that have only one thing in them. So I can have the set that has 0 in it. I could have the set that has 1 in it. I could have the set that has 2 in it. So those are all the possibilities that have only one thing in them. We also could have subsets that have 2 things in them. Okay, so we could have like 0 and 1. We could have 0 and 2. Okay, we could have 1 and 2. They're unordered, so I've run out of options, right? Those are the only options that I have that are sets of size 2. Okay. And I could also have a subset of 3 elements, the whole thing. So 0, 1, 2. Okay. So these are all the ones with 0 elements. These are all the ones with 1 elements, all the ones with 2, all the ones with 3. That's the end of my set. Okay. So what was the cardinality of D? That's 3. And then how many things did we list in the power set? 1, 2, 3, 4, 5, 6. How many?
7.
I hope I listed more than 7. 8, yes. Yeah, there are 8. 1, 2, 3, 4, 5, 6, 7, 8. There's 8.
Oh.
So I didn't think I missed one. Okay. So hopefully you see a pattern here, right? So there's a theorem. So if we have a finite set with cardinality n, so here like we had a set that with cardinality 0, a set with cardinality 1, a set with cardinality 2, etc. Then the cardinality of the power set is what? Can you find a formula? What is it?
2 to the n.
Yes, it's 2 to the n. Okay. So that is a really good way to check yourself if you need to make a power set. If it's got, 3 elements in the set, you know when you're done, you better have 2 to the 3rd or 8 elements in your power set, or you did something wrong. So that's a good way to check. Okay. So these were easier power sets. Now we'll do some more exciting ones. Okay. So we've got a set here, A. It contains 2 things. It contains the empty set and the letter A. So what is the cardinality of A? It's 2. So when we make the power set, how many things are we expecting in the power set? We're expecting 4. Okay. So that will be a good way for us to check ourselves. Okay, so when I do the power set of A, all right, the first thing that can be in there, of course, is subsets of size 0. That's just the empty set. Okay. Now we need subsets of size 1. Okay, so I can have a set that contains this first element. And I can have a set that contains just this second element. So those are all the things that have only one thing in them. So we have one thing of size 0, 2 things with cardinality 1. Okay, and since this has 2 elements, we also should be able to have a 2-element subset. So that will be a set that contains 2 elements. It contains, oh, yep, sorry. So it contains this first element and the second element. Okay. That's an exhaustive list. That's all the sets of size 0, all the sets of size 1, all the sets of size 2. And we do indeed have 1, 2, 3, 4 elements, so that's a good indication that we got them all. All right. Set B is just slightly different. It also, so what is the cardinality of B? is 2, right? So here's your brackets. There's 1 comma in there. So it's got 2 elements. The first element is the empty set. The second element is the set containing the letter A. So notice the subtle difference. It's not, the second element is not the letter A itself. The second element is a set. But it's still 2 elements. Okay, and so when we do the power set of B, we're still expecting to get 4 elements. Okay, so let's do the power set of B. Okay, first of all of the subsets of size 0, there's only one of those. That's always the easy one. Okay, and now I have to have sets that have just one thing in them. So I have a set with this first element in it, or I can have a set with the second element in it. The second element is a set. So the element that's in this set is a set containing A. So notice the parentheses there, or the squiggly brackets there. Okay, I have a set that contains nothing. I have a set that contains this set that is an element, and I have a set that contains this other set that is an element. Okay, could I just throw away these brackets and have it still be correct? No, I could not. Okay, it's very important that the element of this set is a set. Okay, because the letter A doesn't appear in this set. The letter A is not a subset of B. Only the set containing A is a subset of B. Okay, so I got to keep track of those squiggly brackets. Alright, so those are all the sets of size with 1 element. And then of course we have a set with size 2 elements. The 2 elements are the empty set and the set containing A. Okay, and that's the end of our list, and so I got to close this initial one. There's a lot of squiggly brackets in there. Yeah, okay, but you can match them up. These match up, these match up, these match up, these, they're all accounted for. They all have a pair. This is when you wish you had one of those nice editors, like when you program and it matches up the parentheses for you. Yeah. Okay. All right, and now we've got the set, and let's count. Is the cardinality of this set 4? Okay, so there's 1, 2, 3, 4, yes, there's 4 things in there. Okay. So if I want to do the power set of C, which is itself a power set, it might be easier for me to first list out what is in the power set of the set containing A, and after I have that, then I can figure out what the power set of that is. Okay, so the power set of the set containing A, okay, so start with sets of size 0, subsets of size 0, there's only one of those, that's good. And then subsets of size 1, okay, so there's only one of those, and then we're done. Okay, so what do you see about C and B? So here's B. It's got 2 elements. Here's C. It's got 2 elements. Are they related in any way? Yes. What are they? They're exactly the same, right? So B is equal to C, so the power set of B is exactly the same as the power set of C. Okay. So this is the power set of C as well. Lots of little squigglies in there you just got to keep track of. Okay. But if you systematically go 0 elements, 1 element, 2 elements, it's not too hard to keep track of. Okay. Alright, the next concept that we want to look at is union and intersection. And again, this is probably something that you've encountered at some point in your life, so hopefully this isn't too new of a concept to you. So if we have sets, we can combine sets. So I know, like if you do integral notation, you use a union and intersection, and that, you guys have all taken calculus, so I'm assuming you've seen these symbols before. Okay, so the intersection of two sets is denoted with this upside down horseshoe, upside down U looking thing. Okay. It is the set of all elements that are members of both A and B. Okay, so one thing to note is that intersection and the word and, the symbol for and, okay, the symbol for and looks like that. They look really similar. Okay, so and intersection act very much the same. We're going to see a relationship between our logic symbols and our set operators, and we'll see that the intersection acts just like the and. Okay. The union of A and B denoted with it looks like a U, so that's one easy to remember. A, U, B. It looks like a big U. That's for union. Okay. That's the set of elements that are members of A or B. Notice the use of the word or. Our logic symbol for or looks like this. See how they're both down? They look very similar. We will also see that union acts very much like or. They're very similar. Okay. Okay, so intersection, basically that's where they overlap. Okay, it has to be in both A and B, so that's their overlap. And union is I take them both and throw them into a bag and put them together. Okay, so it's either A or B or both. Put them all together. Alright, so going back to this picture that we had before, again, remember that C is this guy right here. So if we want to do A intersect B, okay, well this is the set of all elements that are members of both A and B. So this is going to be a set. And I have to go look. Alright, can you find any things that are both in A and in B? Yeah, 4 and 16. So 4 is in A, it's also in B. We could list that one there. 16 is in A, it's also in B. Okay. Anything else? 1 and 9, only in A, not in B. Any of these, 2, 6, 8, those are only in B, not in A. The only place where they overlap is this 4 and 16. That's their intersection. Okay. If we go to A union B, well that's everything that's in A or B or both, just as long as it's in either A or B or both. Okay. So what are some things that are in A or B or both? I actually even brought, I brought this because I thought this might, so here's A, here's B, so if you just put them both together like that, that's the stuff that's in both A or B or both. Okay, so we've got, oh no, I shouldn't have, alright, so visualize that, I should have turned it this way. Okay, so we had 1 and 9 over here. We had 4 and 16 where they overlap, and then we have all of these over here, 2, 6, 8, 10, 12, 14, 18. Okay, so all of those would fall into that A union B. Okay. What about A intersect C? So things that are both in A and in C. Yeah, 1 and 9. Okay, so 1 is in A, it's also in C. 9 is in A, it's also in C. There's nothing else. So just 1 and 9. Okay. What about A union C? So anything that's either in A or C, or it could be in both. 1, 9, 4, and 16. Okay. Now B intersect C. So here's B over here. Here's C over here. B intersect would be things that are in both B and C. So you're shaking your head. So what should I write here? Yeah, so the empty set. Good. So that would be the empty set. So you can write it that way, or if you wanted to write it this way, you could. Either one of those. They're the same thing. Okay. And then B union C would be it's either in B or in C. Basically take B and C, throw them in the bag together, and everything that lands in there. So what's in B or C?
The same thing as A union B.
Yeah. Good. So we have all of this stuff in B, so 2, 4, 6, 2, 4, 6, 8, 10, 12, 14, 16, 18. And then we also have the 1 and 9. And yes, you're right, Evan, it is the same as this one. They're just in a different order, but it's easier for me to see that way. Okay, and then we have A intersect B, which is up here, 4 and 16. Okay, so that's this part right here. Okay, and then unioned with C. So what would that one be? 1, 9, 4, and 16. So far, all of those are just like maybe unions of 1 or 2, maybe 3 sets. But what if you want to do a whole bunch of sets and intersect a whole bunch of them, or do a union of a whole bunch of them? Well, we have special notation. And this notation should look very familiar. It's like if you had like the sum from I equals 1 to n of I or something like that. So you guys are familiar with summation notation. Or you've probably seen product notation where you have the product from I equals 1 to n of whatever I. So you've seen that notation before, so this shouldn't feel too unfamiliar to you. So it's the same idea. So I've got an intersection from I, start going from 1 to n, and then I have some expression over here containing the index for this sequence of unions here, or intersections or unions. Okay, so notice that this notation is very similar to this. Here I'd be like, oh, I start at 1, and then I just go and increment until I get up to this upper bound. Same idea here. So the index starts at 1, and I'm going to intersect together, starting at 1, a sub 1, that one, intersect, well then I move to the next one, a sub 2, move to the next one, a sub 3, and I don't stop until my index reaches the upper bound, a sub n. Okay, so it's just a shorthand form of writing this big long intersection out. And there's a similar one for union. Okay. So let's do some examples with this notation. So let's say for any integer that is an element of the positive integers, so that would be 1, 2, 3, 4, 5, 6, and on it goes. Okay. The set A with the subscript I is going to be the set of all the positive integer multiples of whatever the subscript was. Okay, so for example, A sub 1, that's going to be the subset that contains all positive integer multiples of the subscript is 1, so all the multiples of 1. What are all the positive multiples of 1? Integer multiples of 1. Is 1 a multiple of 1? Yes. Let's start there. That's the first positive integer, so. Is 2 a multiple of 1?
No.
Yeah. Is 3 a multiple of 1?
Yeah.
Okay, so you get the idea. It's all of these, right? It's just all of the positive integers. So that's what that set looks like. Okay, then we have a sub 2. That will be all the positive integer multiples of 2. So what's the smallest multiple of 2? 2. What's the next set in there? What's the next number in there? 4, 6, 8, 10, on and on they go. Okay. Then A sub 3. 3, 6, 9, you got it. 3, 6, 9, 12, 15. Okay, A sub 4. It's going to be a 4, 8, 12, 16, 20, etc. And A sub 5. Yeah, 5, 10, 15, you got it. Okay, so that's what those sets look like. All right, and so think about it. Those are our sets, and so I'm doing the intersection. I starting at 1, so it's going to be this set. Okay, intersected with this set, this set, this set, but stopping when I get to A5. So I'm going to do the intersection of these 5 sets. Okay. So I might say, okay, well, would 2 be in the intersection? For an element to be in the intersection, it has to be in every single one of them. Like 2 is here and here, but it's not in any of these. 4 is here and here, it's here, but it's not in the A3, it's not in A5. What's the smallest number, like the first place, if we listed these numerically, what's the first place that we would find a number that was in every single one of those sets? Sorry, what was it? A. What do you mean by A1? So, well, mine isn't in this set, so it's definitely not A1, because I already found a number that's in A1 that isn't in the other sets. So it has to be a number that's in every single set.
60?
It's 60. That's right, it's 60. And how did you get 60?
It's like the least common multiple.
Yeah, because we have to find the least common multiple of 1, 2, 3, 4, and 5. Because it has to be a multiple. It has to be in this and this and this. So it has to be a multiple of 1 and of 2 and of 3 and of 4 and of 5. The least common multiple of 1, 2, 3, 4, and 5 is 60. Okay. So when I take the intersection of all those sets, okay, the smallest one that's in there is 60, but the next one, 120, right? So this is actually the set A sub 60. So 60, then 120, then 180, and so forth. All of those would be in there. Okay. All right. Let's say we wanted to do the union of so we're not doing this one anymore because that's just going to give us all the positive integers. But starting at 2 up to 5, so we're going to take all of these and union them together, okay, and then intersect that with integers that are between 1 and 20. Okay, so we can probably just kind of go through them. Okay, so with 1, let me put a little box around. So I'm just talking about these ones right here. And look, it's tech colors. Okay, so ignore that one. All right, so with 1, if I threw all of these in a bag, would 1 be in there? No. Would 2 be in there? Yeah, 2 is in there. Is 3 in there? Yeah, that's right there. 4, that's right there and there. Is 5 in there? Yeah. Is 6? Yeah, I see it a couple times. Is 7 in there? No. 7's not in there. Okay. So, what else would not be in there? Somebody said something, but I couldn't hear it. What was it?
11.
So 11. So 7 wouldn't be in there. 11 wouldn't be in there. What else? 13. Yeah, any prime number after 5 is not going to be in there because those aren't. So we can only have multiples of 2, 3, 4. So they're going to have to be composite numbers. So anything after 5 that's prime is not going to be in there. Okay, so let's just make ourselves a note. No prime numbers after 5. All right, so 7 will be in there. 8, 9, 10 will be there. I already said no 11's prime. 12's good. 13, nope. 14, 15, 16, none of those are prime. 17, that's prime. That's not going to be in there. 18, 19, prime. Not going to be in there. 20. Okay. All right. So those are our basic set operations. We have union and intersection. So intersection where they overlap, union where we put them together. Okay, those are the most common ones, and probably, like, I'm sure you've seen these before, like I said. Okay, we also have some other ones that you might not have seen before. So set difference and the symmetric difference. Okay, these difference is fairly intuitive, and you'll see that symmetric and difference will make sense to you as well. Okay, so the difference between two sets A and B, which we know with like a minus sign, so that makes, it's not like we're changing symbols on you. You're used to minus being difference, is the set of all the elements that are in A but not in B. So basically you start with A, and then you take away anything that's in B. Okay, and then you're left with the things that are in A but aren't in B. So it makes sense, this kind of minus idea makes sense. Okay, so let me get my little, okay, so imagine I was going to do A minus B. Well, here is A right here. And then if I subtract out B, anything that is in B, I'm going to take it away. So 4 is in B, I'm going to get rid of that one. 1 is in B, I'm going to get rid of that one. 3 is in B, I'm going to take that one away. 9 is in B, I'm going to take that one away. So anything that's in B, I'm going to take it out. And then what I'm left with, so notice the 2, the 6, and the 10, that's what I'm left with. So that would be A minus B. The 2, the 6, and the 10 are what I'm left with. Okay. Let's say if I want to do B minus A. Okay, so we start with the set B. And then anything in A, this time we're going to take out. Well, 4 is in A, I got to get rid of that one. 1 is in A, I got to get rid of that. I got to get rid of the 3, I got to get rid of the 9. Okay, all the stuff that's left in there is only in B, it's not in A. So I've taken out all of the A, and I'm just left with 13, 14, and 15. Okay, the next one. Sorry. Okay. We might need 2 colors. Okay, here's A. I'm going to subtract out B, so I'm going to get rid of this stuff. Okay. And now I'm going to get rid of the stuff that's in C. So anything, so here's what I'm left with, my little moon shape, my little crescent moon there. And now I'm going to take out the stuff in C. So this stuff is in C, so I've got to take out that stuff. And the only thing that's left is the 10. So we got rid of everything, and took A, removed everything in B, removed all of that, removed everything that was still in C, and whatever was left is our difference. Okay, so that's difference, and then we have the symmetric difference. Notice the symbol used for symmetric difference. What does it look like? It looks like exclusive OR. It acts exactly like exclusive OR. Okay, so the symmetric difference of two sets is all of the elements that are in exactly one, either A or B, but not both, just like exclusive OR. Right? So just like exclusive OR. It can be in the first set or the second set, but it can't be in both of them. Okay, so let's try that one. Okay, so I need things that are either in A or B, but not both. Maybe I need another color. Okay, so here's A or B, right there, but it can't be in both. Okay, so there is some stuff that's in both. I got to get rid of that stuff. So 4 is in both. Got to get rid of that. 1 is in both. 9. So we got to take out all this stuff that's in both of them. So get rid of that. Okay, so A or B, but not both, is the stuff that's only in A, 2, 6, 10, or only in B, the 13, 14, 15. So this one's going to be our 2, 6, 10 from A, and the 13, 14, 15 from B. Okay. How about B and the symmetric difference of B and C? What's in B or C, but not both? Okay, here 11, 12.
2, 6.
Okay, 2, 6, 11, 12. 4 and 13. Okay, good. So get rid of all this stuff that's in both of them, right? And the stuff that's only in C and only in B. All right, the next one's a little bit trickier. So A and B symmetric difference. Okay, so get rid of this stuff here. And now do the symmetric difference with C. So any intersection with C you got to get rid of. So you got to get rid of that and that. Right, so it's an A or B or C, but not in any of their intersections. So we've got 10 that's only in A. We've got 11 and 12 that are only in C. And we've got 13, I heard somebody say that's only in B, up there. So that would be the symmetric difference of all three of them. Yes?
So it's not like an order of operations then when you do A and B and then C. It's like both of them at the same time.
Well, you would do it. You would do A and B, and you would get rid of that. And then when you symmetric difference that with C, you would do that. But I think symmetric difference is associative, so it turns out that you can do it the other, yeah. Okay. But normally you would do it left to right. Okay. We will talk about order of operations, but from what we know, from what I've said, telling you that like and is like intersection, or is like union, we've got this exclusive or, you can kind of tell there's going to be an order of operations. Intersection is going to have to be done before union if you list them out, like all the things that we've seen before, it'll be the same. Okay. The other one that we want to talk about is set complement. So the complement of a set denoted by putting a bar over it, and we've already kind of seen this notation with rational numbers and irrational numbers. So rational numbers is, think about this is rational. And how do we denote irrational? Well, we just put a bar over top of it. Okay, so if you think about what that means, we have a universe of real numbers. Okay, we've got this set rational, and everything that's not in that set in our universe is in this one. Okay, so we've already sort of thought about that concept. So that's the complement, set complement. Okay, so it is the set of all the elements in the universe that are not in A. Okay, and so notice this kind of looks like that, right? So it's like the not operator. Okay, so my universe is everything in this rectangle. And so if I do the complement of set A, well, here's A. So everything that's not in A, I just got to cover up, okay, well, that's A. If I got rid of all of A, then all this stuff out here is not in A. So I've got this 5, 7, 8 that's not in A. And then I've got this 11, 12, 13, 14, and 15 that are not in A. Okay. So it includes this stuff too, that's in the universe and isn't in any set. So make sure you look at the entire universe. Okay. All right. What's in not B? Yell them out, I'll write them down. 10.
2, 6.
2 and 6. 5, 7, and 8. 11 and 12. Okay. None of those things are in B. Okay. All right. Next, we've got A union B, and then we'll take the complement. Okay. So do I have a All right, here's A union B. Okay, so we need everything that's not in that. So what are those things?
5, 7, 11, 12.
5, 7, 8, 11, and 12. Good. So everything that's not in there is all this stuff down here. All right. A intersect C. Okay. So A intersect C. That's the stuff that's common to A and C right in here. Okay. And then we need not that. So not anything that's in A intersects C. So what are those things?
10.
10. What else? 4 and 13. What else?
15, 14.
15 and
11.
15, 14, 11, 12, 5, 7, and 8. Good. Okay. So you just kind of went around that way. Looped around. All right. So B, symmetric difference C. Okay, we might have a picture for that one. Okay, that was our, maybe if I turn it this way, it won't go up. Okay, forget that one. All right, so B, symmetric difference with C. So we got rid of that stuff and put that, so that stuff. And now we need to do the complement of that. So what would be in the complement of, maybe I'll just, so B, symmetric difference with C is everything that I'm putting in red here. It's there and there. Right, that's the symmetric difference. Stuff that's in B or C, but not both. So what is in the complement of that?
1, 3, 9, 14.
1, 3, 9, 14, 15. Anything else?
5, 7, 8, 10.
5, 7, 8, and 10. Okay. Good. So, if you're a colored pen person, that might help you keep track of those things. Yeah, we've got time for, we won't finish this, so we aren't going to finish section 2.5, but we've got 10 minutes, so we might as well restart it. So for next time, so today is Thursday, for next Tuesday, you will need to finish up through 2.4 from Zybooks. I will try to put an announcement, okay. And then next Tuesday, I also would like to have at the end of class a quiz over the stuff from chapter 1 that wasn't on our last test. So that's like nested quantifiers. Okay. So where you have, flaws and, there exists together, not just one variable, but multiple variables, as well as like those special things like exactly one and everyone else, those kind of tricky notations. I'll put an announcement on, but that's going to be on Tuesday, the rest of chapter 1 that we haven't been tested on yet. Eventually we'll do a set 1 as well, but not yet. Okay. So, yeah, as I mentioned, there is a relationship between sets and logic. So we'll see a lot of the things that we've already done in logic will easily translate into sets. And like I mentioned, the and the intersection are very similar. The or and the union are very similar. Complement and negation are very similar. Okay, so we can define the set operations in terms of logical operations. So here what we're saying is X is an element of the intersection of A and B if and only if, so this is like our biconditional here, if and only if X is in the set A and X is also in the set B. Okay, so the only way for an element to be in the intersection is if it's in both A and in B. So this has to be true and this has to be true. This has to evaluate to true in order for this to evaluate to true. Okay, if this evaluates to false, it's not in both X and A, then this one will also be false, right? So these will always have the same truth value. Okay, similarly, X is an element of A union B if and only if it's an element of A or it's an element of B. So notice the relationship between union and or. Okay, whenever this one evaluates true, X will be in the union. If this were to evaluate to false, it's not in A or in B, then it can't possibly be in the set with putting them both together. Okay. And here, X is in the complement of A if and only if it's not X is in A. So if this, X is in A is false. So these would be the definitions. So how you can take a set operator, basically, and define it in terms of logic operations. Okay. We can also say that X is in the universal set if and only if true. Okay. X is always in the universal set. So if X is in the universal set, this is true. If X is not in the universal set, that would be, okay, that's false. Okay. And then X being in the empty set, well, there's nothing in the empty set. Okay, so this is always false. There is nothing in the empty set. So false will act very much like the empty set, and true will act very much like the universe. Okay. And so we basically made this connection between set operators and set concepts like the universe and the empty set, and these logic operators and logic concepts. Okay. And so we can use the logic definition, the logic operators, to make set identities that will be basically equations involving sets that will be true regardless of the contents of the set. We don't have to know what the sets are. We can just logically prove these certain identities about sets. We'll just do one of them and then we'll be done, and next time we'll look at all the rest of them. Okay, so De Morgan has a set identity. So we know De Morgan's identities for logic. So if we do not A and B, recall, we not the first thing, we change the and to an or, and we not the second thing. If we have a disjunction instead, we not the first thing, change the disjunction to conjunction, and do not B. We'll see something very similar happens, okay, for these. So if I want to say X is an element of this set, A and B. Okay. So how can X be in the complement of a set? Well, notice here's the definition. X is in the complement of the set if and only if, so this is only going to happen if it's not in that set. So if it's not, X is in, well, what set are we talking about? A intersect B, sorry, intersect. Alright, so now we have A is an element of A intersect B. We know that A is an element of A intersect B only if it's both in A and it's in B. So we can replace this with its equivalent definition. So X is in A and X is in B. And now we've changed from, talking about a set into completely logical. So we have not, proposition, and proposition. Everything's in terms of logic. Okay. And we know how to deal with logic. We just do De Morgan's laws for logic operators. So not the first thing, so not X is in A. And then we change the and into an or. And then we do not the second thing. Now if we go back and look at our little definitions here, so this not X is in A is exactly the same thing as X is in A bar. So I can replace this with X being in the complement of A, and I can replace this one with X being in the complement of B. And And then once again, I'll go and look, well, if I have X is in one set or X is in another set, I see that right here. Well, that's the same thing as X being in the union of the two individual sets that we're talking about. So this is exactly the same as X being in the union of these two individual sets in question. Okay. And so now what I see is if X is in the complement of A intersect B, that's exactly the same thing as saying that X is in the union of the complement of A and the complement of B. So this is exactly the same as this. Looks just like De Morgan, doesn't it? Okay, so when I have this complement, I complement the first set, I complement the second set, and I change the intersection to union. Okay, so you should be able to tell me, without going through all of the crazy logic, okay, what is this one going to be? The complement of A intersect the complement of B, exactly. So that's what De Morgan tells us, and you can see that it's really very similar to logic. I'm just going to complement the first one, change the intersect to union, complement the second one. Same thing here. I'm going to complement the first one, change the union to the intersection, complement the second one. Okay. And next time we'll have a very exciting set of set identity laws like this. We've seen these before for logic, but now we have them for sets. And then we can do proofs about set identities instead of logic tautologies and things. So those are the exciting things to come, but we're out of time for today.
So let me take a test on that.